Today we'll discuss the branch instructions of ARM. Okay. First, we'll see what is the purpose of using branch instruction or what is the application of branch instruction. Using branch instruction, what we can implement, what structures of C we can implement using branch instruction, and what happens once a branch instruction is executed. So what will be the status of PC once branch instruction is executed? And we'll list out the branch instructions supported in ARM, and we'll see what is the execution effect of after executing those branch instructions. This is what we are going to cover in this session. This is the purpose of using branch instruction. You can use branch instruction to change the flow of execution or to call a subroutine. So if you want to deal with multi-function program, okay, several subroutines you want to write, in that you want to transfer the control to the subroutine, then also you can make use of branch instruction, or within the same program, within one program itself, if you want to transfer the control from one point to another point in the program, we can make use of branch instruction. So a branch instruction is used to change the flow of execution or to call a subroutine. Okay, this is the application of branch instruction. The branch instruction, it allows the programs to have subroutines, if then else structures and loops. So using branch instructions, what and all you can implement, you can go for having multi-function program, or you can have if then else structure implemented. So if this condition is satisfied, transfer the control to some point to execute the statement, or else transfer the control to some other point in the program. So how to implement if then else structure, we shall see with the example. And the looping, already we have used branch instruction for repetitive process, right? So to implement loop or to construct loop, we can use branch instruction. To call a subroutine, we can make use of branch instruction, and to implement if then else structure, we can make use of branch instructions. Okay, so once branch instruction is executed, you know that the program counter, so which will be always pointing to the next instruction to be fetched for execution, so that address will be changed. So PC will be holding the new address that is called as the target address. So whenever a branch instruction gets executed, so if it were to be conditional branching, so once the condition is satisfied, PC will be loaded with the target address. If it were to be unconditional branch instruction without testing any condition, PC, the current content of PC will be replaced with the target address. So this is what you need to remember. So branch instruction is going to change the PC content to the new address, which is called as the target address. Move on to the instructions supported in ARM for in the branch instructions category. So these are the four different branch instructions. In ARM version 5E, these are the instructions supported, and these are all upward compatible, where ARM 7 processor can also execute these instructions, that is B, BL, BX and BLX. So these are the four mnemonics you need to remember with respect to branch instructions: B, BL, BX and BLX. Coming to the syntax of these four branch instructions, B, you can see, as I already mentioned, whatever you specify within flower brace, it is optional. B is the mnemonic we are using, and if you want to give the condition attribute for this, you can specify. Followed by that, you are going to give a label. This we have already used in the lab syllabus programs, wherever repetition is required. We are testing the condition with the condition attribute any we have used, right? That is optional. If you are not specifying, it becomes unconditional branch instruction. So if you want to make it conditional, you are going to specify the condition attribute in addition to the B mnemonic. Okay. This is one syntax for the B mnemonic supported. B condition attribute followed by that label. Next mnemonic is BL. BL condition attribute label. Just observe the operands what we are specifying for these branch instruction, and whether you can give condition attribute for the branch instruction or not, that you need to observe in each of these syntax what we are listing. Okay. BL is the mnemonic we are using, condition attribute you can give, and followed by that you are going to specify the label. Observe the third mnemonic, BX, branch and exchange, where we can specify the condition attribute for this also. But what is the operand you are specifying for BX instruction? You cannot give a label here. It has to be a register which holds the address, the target address. So this is what you need to know. BL, where the operand can be the label, must be the label, whereas BX instruction, the operand must be a register which holds the 32-bit register which holds the target address. Okay, and for each of these three instructions, we can specify the condition attribute. And yes suffix will not give for branch instructions. Remember, branch instructions will not affect any of the flags except control flag. In the control field, you are having T bit. In two instructions, BX and BLX, it may affect T bit. Based on the RM register content, it may affect the T bit. But conditional flags will not be affected when branch instruction is executed. That's why you can see in the syntax what we are listing, we are not having yes suffix. So we should not give yes suffix for the branch instructions. Okay. BX condition attribute, RM is the syntax for branch exchange. Next, the last instruction is BLX, and there are two forms of BLX, one with the operand as register, another with the operand as label. Just observe the last two syntax specified with respect to BLX. BLX is the mnemonic, then we can specify the condition attribute. Followed by that, you can give the register as the operand. This is one syntax of using BLX. The other syntax is BLX label, where we cannot specify the condition attribute. So just see, first four syntax, whatever we have mentioned in that condition attribute can be given to the instruction. That means these branch instructions can be conditional branch instructions, whereas the last branch instruction specified, it will be unconditional. So without testing any condition, once BLX instruction is executed, control gets transferred to the label wherever it is defined. So this is another form of BLX. Okay, and you should not give any condition attribute for this last form, where label is specified as the operand, whereas last but one syntax, what you are saying, if it were to be the register as operand you have taken for BLX instruction, then condition attribute can be given. And what is the difference you are finding? First, I'm trying to list out the main differences in these branch instructions. Later on, we shall see still more details with respect to each of these branch instructions. See, in BL and BX instructions, what you are seeing. So you are seeing the mnemonic BL, BX, BLX you are seeing. So wherever L is there in the mnemonic, it means branch and link in this mnemonic. So once this instruction is executed, the written address, that is the address of next instruction after branch, that written address will be saved in the LR register. That is R14, which is the link register. So remember, wherever L is specified in the mnemonic, in addition to transferring the control to the target address, they are also going to save the written address in the link register. This is what happens in BLX and BL instruction. That's why that is branch and link. So once I say branch and link, the written address will be saved in the link register. This is what you need to remember. So what are the points at this point you have to remember? Totally four mnemonics are supported in under branch instructions category: B, BL, BX, and BLX. These are the four mnemonics. For branch, that is B, BL, and BX, we can specify the condition attribute. For BLX, if register operand is specified, then only we can give the condition attribute. If you are specifying the label, then you cannot give the condition attribute. This is one point you need to remember. And one more is the L suffix, what we are seeing for the branch instruction. L letter that indicates branch and link, where link register comes into picture. So before transferring the control to the target address, the written address will be saved in the link register. This is what you need to remember. So just see a few more details are specified in this table. The four instructions are specified: B, BL, BX, and BLX. B stands for branch, BL branch with link, BX branch exchange, and BLX branch exchange with link. So remember, this BX and BLX are actually the instructions which can be used for switching over the state of the processor from ARM to thumb and vice versa. So to inter working of the state, we can make use of BX and BLX instructions. So since it is out of the scope of a syllabus to discuss about the thumb instructions, so just we shall try to describe this BX and BLX instructions. Okay. Just see the last column in this table. Branch, this is unconditional branch instruction. If you want to make it as conditional, as I told, you can specify the condition attribute, that is, you can suffix it after B. Once this instruction is executed, PC will be loaded with the target address. The label address will be assigned to the PC. Control gets transferred to the label wherever it is defined. So this is about branch instruction. If you are giving conditional attribute, then only if that condition is satisfied, PC will be loaded with that target address. Coming to the BL instruction, branch with link, just observe the difference between first the mnemonic and the second. Here, if you use branch instruction B label, in that case, the return address will not be saved in the link register. Whereas BL instruction, which you have already used in the factorial program, where to transfer the control to the subroutine, what happens is before the control is transferred to the subroutine, the return address, the address held in the PC, that will be saved in the link register. So LR is loaded with address of next instruction after the branch instruction BL, and PC will be loaded with the label address. Then the control gets transferred to the subroutine and it executes the statements. So this is about BL, branch with link. So B and BL will work with ARM instructions. Okay, if you want to work with ARM instruction and thumb instructions in the instruction set executions, then you can make use of BX or BLX instruction. So BBL are dedicated for ARM instruction set execution. Okay. Coming to the BX instruction, branch exchange. See, here it is not going to save the return address in the link register, as you can see in this table. PC will be loaded with the result of this AND operation. And you can see BX instruction, the operand considered is the register. It takes the register what you have specified in the operand. It performs AND operation with this value, that is all 7 Fs, and E is the least significant hex digit. So what operation performed here is AND operation, where it is forced to have the bit 0 in the RM register. So it just makes bit least significant bit as 0. That value will be loaded to the PC. So this is what the operation performed. So that means the PC will be having the address to where the control is to be transferred to. And since it is 32-bit instructions in ARM, okay, the least significant bit will be always 0. It will be 32-bit aligned. Each word will be 32-bit aligned. And just remember that PC will be loaded with this result of this operation, RM and 0x7FE, where bit 0 is forced to be 0. That value will be loaded to PC. And T, this is the operation performed to set or reset the T bit. Then if the bit 0 of RM register, if it is 1, 1 and 1 will result in the value 1. That means the T bit in the CPSR register, which is the thumb bit, which is in the control field of the CPSR register, that will be set to 1. That means the state of the processor gets changed to thumb state. So if in the RM register, the LSB bit is 1, performing AND operation with 1 will result in value 1. That will be loaded to the T bit in the CPSR register, which changes the state of the processor to thumb state. If RM bit is 0, then it will be in the ARM state. So this is what you need to know with respect to branch exchange instruction. PC will be loaded with the result of AND operation, RM and 0x7FE, and T bit will be loaded with this status. If bit 0 of RM register is 1, then the T bit gets set to 1, which changes the state of the processor from ARM state to thumb state. Okay, if bit 0 of RM register is 0, then T bit will be 0. That means it will be in the ARM state. Coming to the BLX instruction, branch link, that is branch exchange with link, as the name itself indicates. Here link register comes into picture. And there are two alternative forms of BLX instruction that I have listed in the syntax here. Last but one and last syntax you can see. Once this BLX instruction is executed, PC will be loaded with either the label address or whatever the address held in RM register. This is one operation performed. So what is the operation performed? The address, the label address, if this is the last syntax if you are using, then the label address will be assigned to PC or loaded to PC. Or if you are using the last but one syntax, then RM register content will be loaded to the PC and control gets transferred to that location, to that target address. This is one thing. And one more point is, if you are using and the written address, so here since BLX instruction is used, whether you use last but one form or the last form, since BLXL letter is available in the mnemonic, what it means is the written address will be saved in the link register. That is R14 register is the one which holds the written address. This is one point. So any of these two syntax you use, BLX with RM as the operand or label as the operand, it is going to save the written address, which is address of next instruction after BLX, into the link register. This is one thing. If it were to be using the last but one syntax where rm as the operand, if it considers, then it is going to load PC with what address? It is the result of AND operation, rm and 0x7fe. So the result of AND operation is loaded to PC. If it were to be the label as operand you specified, then that target address will be assigned to PC. This is the next point you need to remember. First point with respect to BLX, remember there are two alternative forms of BLX. One as register operand, other as the label. Okay, this is one point. Another point is the written address will be saved in the link register. Any of these two forms you use, written address will be saved in the link register. And one more point is the PC will be loaded with the label address if you are using the last syntax, or PC will be loaded with RM and 0x7fe with this result if it were to be last plus one syntax you are using. This is the next point you need to remember. And whether the state of the processor will change or not. So if it were to be the label as operand you are considering, then T bit will be set to 1, which changes the state to thumb state. ARM state, from ARM state, it switches over to thumb state. If the last syntax we are using in the BLX instruction, but if you are using the RM as the operand in the BLX instruction, then it performs this AND operation. The least significant bit of RM, if it were to be 1, then only the state of the processor will change to thumb state. Otherwise, it will be in the ARM state. So this is what the points you need to remember with respect to BLX instruction. With respect to each of these two forms, BLX with condition attribute RM and BLX label, these points you have to remember. So that's what been summarized in this table. Totally 4 branch instruction, B, BL, BX, BLX. BLX is having two forms, one without condition attribute. It is an unconditional branch instruction with link exchange you are having. Other one is with conditional attribute we can specify in the BLX instruction. And just observe the operands. One can be register, other can be the label. And what happens once these two forms of BLX instructions are executed. So this is what you need to remember with respect to these 4 branch instructions. Same thing I have summarized here. The branch instruction B, label. So this is the first branch instruction what we have discussed. Once this is executed, it causes the branch to the label address. BL instruction, it copies the address of next instruction after BL, which is called as a written address. That will be copied to the LR register, and it causes the branch to the label specified in the instruction. Coming to the label. So this label, what you specify, how it is encoded in the instruction. You know, each instruction is ARM is 32-bit. Out of this 32-bit, the machine code generated, actually 24 bits will be reserved to specify this address of the label. Okay, and it will be actually PC relative offset. So from the current content of PC, at which address the target is available. So that distance from the current PC content or current PC to where the target is available. So that signed data that will be encoded in the machine code. Okay, so it may be positive if the label is appearing before the branch instruction, then it will be negative offset stored in 2's complement form. If the label is appearing after the branch instruction, then it will be positive offset that will be encoded in the machine code. And this distance will be approx within 32 megabyte of the branch instruction. This is approximately around 32 megabyte. The distance from the that is the where PC is pointing to the target address. So this is what you need to know with respect to the label. Coming to the T bit, that is the thumb bit in the CPSR, as I already mentioned, with respect to BX and BLX instruction, if bits 0, the least significant bit of RM is 1, then T bit in the CPSR register will be set. so that the arm switches to thumb state. That is the code at the destination. Once the control gets transferred to the destination location, it is that code is interpreted as the thumb instruction set. If bit 0 is in the bit 0 of RM is 0, then it will be in the ARM state itself. Then BX instruction, coming to the BX instruction, it causes branch to the address held in RM. You know BX, for B and BL, operand is label. For BX instruction, operand is the register. So whatever the address held in register, to that the control will be transferred to. That means PC will be loaded with the data held in RM register, and it changes the instruction set to thumb state only if bit 0 of RM is set. That is RM and 1 is the operation performed to change the state of or to change the status of T bit. So if RM least significant bit of RM is 1, then T bit will be 1, otherwise T bit will be 0. Coming to the BLX instruction, as I told, it is having two alternative forms, BLX label and other one is BLX with RM as the operand. BLX label is the unconditional branch with link to the label address. We are not specifying any condition attribute for this. And this instruction, it copies the address of next instruction after BLX into LR, and it causes the branch to the label. Not only it does this, it also changes the state to thumb state. T will be explicitly set to 1 if this syntax for BLX is used. So BLX with condition attribute RM is used, then only if the result of AND operation between RM and 1 is 1, then only it changes the state to thumb state. And this also copies the address of next instruction. The return address is copied to the LR register. These 2 points are summarized in this next point. BLX instruction, what it does, copies the address of next instruction into LR, causes branch to either label or to the address held in RF, and it changes the instruction set to thumb code if either bit 0 of RM is set, or if it were to be the second syntax you are using for BLX. Otherwise, BLX label form if you are using, then explicitly without testing any condition, it changes the state to thumb state. So what you have to notice, BX and BLX instructions, they cause a switch between ARM and thumb state while branching to the subroutine. So once T bit gets set to 1, the destination to where the control gets transferred to, remember that would be the thumb instruction set that would be executed. Coming to the two different two types of branching which are possible using branch instruction. That is, you can either have backward jump or forward jump. In backward jump, as you know that the label appears before the branch instruction. Using this backward jump concept, we can go for creating the loop. So repetitive process can be achieved using this backward jump concept. And in forward jump, the label appears after the branch instruction. I've considered one simple example for backward jump. This we have already discussed. Example to compute the sum of first n natural numbers. Okay, move R0 with hash 5, R1 with hash 0. Assume I want to compute sum of first 5 natural numbers. Initial sum I have taken in R1 as 0. So we are computing the addition operation. See, loop label you can see, and R0 as a counter we have used, SUBS instruction we have used, branch not equal. This is the conditional branch instruction we have written. If 0 flag status is 0, control gets transferred to the loop label. This process is repeated. So this is an example for backward jump where the you can observe label is appearing before the branch instruction. See, BNE loop where loop label is before branch instruction. So this is called as backward jump. If Z is 0, then only the control will be transferred to the loop label. So this is called as backward jump. So we can also achieve forward jump. In this example, another same program, another version of the same I'm showing in this slide, where we are using both backward jump and forward jump. So using forward jump, actually we cannot only forward jump, we cannot achieve the repetitive process, but in combination of backward and forward jump, you can achieve that is the looping operations. You can see in this example, usually we use backward jump for looping, but if you want to go for both backward and forward jump for looping, that's also fine, as you can see in this example. Move R0, hash 5, R1 with 0, loop label I have given. add R1 comma R0, then the loop counter is decremented. Now if the Z flag gets set to 1, I'll transfer the control to the stop label. See, this is forward jump I'm doing. If after performing the subtraction operation, if Z flag gets set to 1, then we'll transfer the control to the stop label. Otherwise, I will give an unconditional branch instruction, that is branch to loop label. See, forward and backward both are shown here. So stop label I'll give, where I'll make the control stay in that branch instruction itself. Just observe backward jump, branch to loop. I hope you are understanding how this code is being executed. After the counter is decremented, I'm testing the Z flag status. If Z flag gets set to 1, control gets transferred to the stop label. Here you can observe the label is appearing after the branch instruction. BEQ stop is there. Stop label is given after the branch instruction. This is forward jump. If this condition is satisfied, it makes a forward jump. But branch to loop, this is an example for backward jump. So if BEQ instruction is not executed, control will go to the immediate next statement. This is an unconditional branch instruction I've given, branch to loop. So control gets transferred to the loop label and it repeats the process. Each time it tests whether Z flag is 1. If Z flag gets set to 1, then control gets transferred to the stop label. Otherwise, it keeps on repeating the loop unconditionally. Okay, so both backward as well as forward jump you are seeing here. Once Z flags get set to 1, control will be transferred to the stop label. Okay, this is possible. It is left to you whether you want to use both backward and forward jump for repetitive process or only backward jump for looping implementation. So here you can see if then else construct. See, if this condition is satisfied, BEQ, if the condition is satisfied, then transfer the control to the stop label, else transfer the control to the loop label. This is actually implementation of if then else construct in whatever we have learned in C. Okay, that can be implemented here. Using only backward jump, we can have looping. Okay, or if you want to transfer the control to the subroutine, that is possible using branch instruction, BL instruction. You can make use of. If you want to implement only that is a repetitive process, usually we go for backward jump only. Okay. One simple example on subroutines. So this can be the possible question which you can expect under branch instruction. You may be given with a problem for performing that specific operation. You may have to define a separate subroutine and you may have to make a call to that subroutine. As an example, I have taken this simple problem. Develop an ALP to compare two numbers held in R0 and R1. Design subroutine to compare two numbers and store 10H in R2 if they are equal and store 20H if they are not equal. See, this is the complete program we are implementing. We are loading the initial values to R0 and R1. Say 5 and 10 I want to compare. Now I'll make a call to compare function or the subroutine using DL instruction. DL compare. After that, I've given stop branch to stop. Once DL instruction is executed, the return address will be saved in the link register and control gets transferred to this target address, that is to the subroutine. PC will be loaded with this target address and control comes to this. So first instruction, compare R0, R1, and then we can use this condition at EQ. If the numbers are equal, R2 is loaded with 10H. If the numbers are not equal, R2 is loaded with 20H. Okay, this is the operation that can be performed. And then we can transfer the control back to the calling function using DXLR or move PC, LR. So that instruction can be used. So this is how we can implement. Any question may be given on subroutines, right? Finally, end. So this completes branch instruction.